In this video, I will go through the steps you would take to orient your grain along the fast and slow rays of a mineral. First, you will need to work in cross-polarized light. Here, I insert my analyzer. The grain we see is displaying first-order interference colors in cross-polarized light. Remember from the last video that interference colors are a product of retardation. Retardation is the amount that the slower ray lags behind the faster ray. In order to distinguish between the slow ray and the fast ray, we use an additional tool called the accessory plate. This plate is usually made of gypsum. It has a fixed orientation such that the gypsum's fast ray is parallel to the direction it is being inserted. Inserting the accessory plate can lead to an increase or decrease in retardation depending on orientation. Here, I insert my accessory plate. Inserting the accessory plate will make the material appear magenta at the extinction positions because the plate's retardation displays a first-order magenta. This is the view of the same mineral with the accessory plate inserted. Here, our mineral now displays second-order interference colors. Now, I'm going to rotate the stage 45 degrees to observe what this mineral looks like in an extinction position with the accessory plate inserted. You'll notice that it is magenta instead of black. The slow and fast rays are aligned with the lower and upper polarizers. This is why no light passes through and the mineral is extinct in this orientation. I rotate the stage another 45 degrees to the next maximum illumination position where the slow and fast rays are at 45 degrees from the polarizer directions. Here, our mineral is displaying first-order interference colors. One of these maximum illumination positions is where our fast ray is propagating, and one of these positions is where our slow ray is propagating. Let's look at each position separately. In this position, we go from first-order interference colors in cross-polarized light to second-order interference colors with the insertion of the plate. This increase in interference color is due to the fast ray of our mineral aligning with the fast ray of the gypsum accessory plate. The aligning of the fast ray of the plate with the fast ray of the mineral causes an increase in the lag between the slow and the fast ray, which results in an increase in retardation and interference color. Next, we examine the changes occurring 90 degrees away at the next maximum illumination position. We go from first-order interference colors to first-order interference colors. The aligning of the fast ray of the plate with the slow ray of the mineral causes a decrease in the lag between the slow and the fast ray, which results in a decrease in retardation and interference color. Let's try an example of a mineral grain in a thin section. First, we start out in plain polarized light. Let's perform this exercise on the large white mineral in the center of the field of view. Here, we insert our analyzers and observe the interference colors in cross-polarized light. The striping that you are observing are zones in which the mineral grew, similar to tree rings. Now I will insert the accessory plate. Here I will rotate the stage such that I am switching between where the fast ray and the slow ray is. See if you can determine which is which. If you said fast ray along this orientation, you are correct. If you said slow ray along this orientation, you are correct. So why do we care? Some types of mineral grains display different color or relief along their fast or slow rays. In this snapshot of this pleochroic mineral, where the accessory plate is inserted, take note of the interference color where the arrow is pointing. Also take note of the interference color 90 degrees away. As I switch back to plain polarized light, notice the color of the mineral in this orientation versus this orientation. For pleochroic minerals like the one being shown here, we can describe relief and color in plain polarized light along a fast or a slow ray. With this, you can fully characterize a given section of a mineral. In the following videos, we will learn how to fully characterize a mineral considering all possible orientations in 3 dimensions. Here are some things to remember and some helpful tips. Remember that when using a gypsum plate, extinction positions will display first-order magenta interference colors. Oriented along the fast ray, your mineral will show an increase in retardation and interference colors. Oriented along the slow ray, your mineral will show a decrease in retardation and interference colors.